How's it going, everybody? Thanks for coming. My name's Nick. I'm an engineer at Google, and I work on Tensorflow.js. And I wanted to kind of talk about some themes with machine learning that's kind of changed a lot, and why it's really interesting to especially the front-end developers, full-stack developers in the JavaScript space. Those that read the news, you'll see tons of headlines like this. ML and AI is a very common theme in the industry, and especially in tech news, things that you might read online. Here at Google, we use AI and ML for a ton of our products. This is our current line of hardware offerings. Actually, I think it's kind of old now. That looks like a Pixel 2. So, but outside of like stuff that's in our cameras, smartphones, camera sensors, even things like that big speaker, that's the Google Home Max, and it actually has a TensorFlow model that sits in it. So wherever you put it in the room, it uses a model to automatically calculate the frequency and tunes the audio. And that was just a model that we ship in consumer products. Even in our software products, like the Gmail Smart Reply, we know how to sort of essentially guess what the next sequence of text and help with assistance like that. Translate, image recognition, being able to translate text to your language of choice is all a machine learning model. And of course, self-driving cars are very popular these days, and they're all built with machine learning models. It uses AI. This is a sort of a simulator of what a ML model would be seeing in a self-driving car. Now, if we step back and look at our industry, the spike in the jobs that use AI or require some sort of machine learning continue to keep growing. And if we look at trends in the industry too, Python is sort of a really high up there with R for the language and framework you would use to write machine learning. But on the other hand, if we look at the GitHub pull request, JavaScript by far is twice as popular than Python. And so we thought we might be onto something. This is a project our team built almost 18 months ago now, I think, maybe even 2 years ago. It's called the TensorFlow Playground. It was an educational tool we built to sort of help people who are getting into the space understand what's going on with a deep neural network. So in this demo, there's two fully connected layers of neurons, and there's different activation functions, and you can see how the data tries to plot to that circle on the right-hand side. And this is a demo built by some of our colleagues, and it was all JavaScript and powered by WebGL. And we thought we might be onto something here. Focusing on in-browser machine learning. There's a lot of unique opportunities we thought about. One is you don't need any drivers. Everything just kind of works in the browser. That's one of the great parts of the web. It's very interactive by nature. And we have access to tons of data like sensors. And through smartphones, these are all becoming very common public web APIs. And one of the other really interesting parts is you can do data and training directly on the client. So there's no need to send a bunch of data back to a server-side Python job to do your processing. It's very interesting from a privacy standpoint. All the data can be stayed locally on the client. So jumping back to the TensorFlow Playground, this is about 400, 500 lines of JavaScript code, and it was all special built for this particular project. So in our Google research team, we built this project called DeepLearn.js and open sourced it August 2017, now that's 2019. And this is a linear algebra library that brought machine learning to the web, and all powered by WebGL, and allowed a lot of training and inference. And this is our first stab at this project. And we took it and we aligned it with the goals here at Google with TensorFlow as part of our machine learning ecosystem. We aligned it with our current thinking for what we call eager-based execution instead of graph-based execution. Those are kind of in the weeds type terms, but it's aligned with the future direction of where we're going with TensorFlow. And once we launched this project, we had tons of really cool demos and applications that came out. One of them is Teachable Machine. It's a in-browser labeling, image labeling application that lets you train green, purple, and that looks red, but orange. And so you collect picture frames and can train labels like this. We actually have this tomorrow at ForwardJS as a code lab, I'll actually be building this application one-on-one. So there's 3 models we'll actually work on tomorrow, and this is one of them. This is a community-built application. It's a self-driving car, self-driving GIF car, I guess. But it drives around and it learns how to train all in the browser. One of the other really cool things that's come out very recently, Uber uses a ton of machine learning for all their data and client-side applications, and they've built a whole visual debugging tool using Tensorflow.js called Manifold. They recently published a blog post, I think it was either this week or last. Internally here at Google, one of our research teams is called Magenta, and they're all about generative music. Recently, they launched this plugin for Ableton, which is a music software, like a DJ music software. And they also released standalone versions of their generative applications. So these are actually Electron apps that all use Tensorflow.js for the GPU acceleration. So super cool stuff. Clinic Doctor is I think they're based in the UK, and they provide services for your node stack, GC, memory, and all that sort of business. And they use TensorFlow.js to help filter out GC spikes and node processes to figure out if it's actually a real CPU spike or if you're stuck in garbage collection. So very interesting things that are starting to come in the industry with the project. And what can we do with TensorFlow.js? Well, today you can write models directly in the browser or under Node.js. And we have the ability to bring pre-trained models that have been trained from some other traditional like Python infrastructure and run them directly in the browser. We also have the ability to retrain models, or what we call transfer learning. So you take a model that's been pre-trained and you can skew it to your set of data. On our website, you can find a demo of Pac-Man. We actually have Pac-Man, but you don't play it with the controls on the keyboard. You train up, down, left, and right from pictures you collect from your webcam. So like up, down, left, and right. It's an interesting usability exercise. It's kind of fun, so I invite you to try it out if you have a break. And I want to show the architecture of what we have. So we sort of have 3 components these days with TensorFlow.js. The first one is the Models API, which is out of the box, ready to use machine learning models. You don't have to do any training. And most of these have like a really friendly user-facing API. You don't have to convert data to tensors. You say, here's an image, is it a hot dog or not? So pretty cool stuff. Then we also have our Layers API, which is our Keras style like API for easily writing new models from scratch. And in our code lab tomorrow, we'll be doing interacting mostly with the Layers API. And then diving even deeper, we have our Core API, which is our linear algebra library, and it gives you access to do things like k-means or random forest if you needed to dive at that level of data. So inside the Core API, we're powered by 2 different things. In the browser, we use WebGL currently for our acceleration of our models in linear algebra stack. And on the Node side, we actually ship the same C library we use for Python. And that gives us acceleration on AVX instructions with CPU, GPU with CUDA, and then eventually the TPUs we offer with Google Cloud. For the next couple slides, I'm going to walk you up kind of through the stack of what we have. So this is the most in the weeds type example of using our Core API. So a very basic machine learning problem is just trying to fit, you probably did this at one point in college or algebra or calculus or whatever. So these are a plot of lines of data we have, those little blue dots, and we're going to write a model that learns to find that blue line of curve, like where does the data actually turn and have that curve. And that can be solved with the polynomial ax squared plus bx plus c. So looking at it from some code, we're going to import our package, and we have a union package called @tensorflow/tfjs. That includes our layers, our data API, and everything. The first step is to declare 3 different variables, a, b, and c, and we're going to initialize them as a non-zero value. And then finally, defining that polynomial will look like this. Thankfully, we have dot notation in the API, so that's a little cleaner. The next step is to declare a loss function. We're going to use the mean squared error loss function. And then we will use that in our optimizer. We're using SGD, which is the stochastic gradient descent algorithm. It took me about 2 months to get that down. And that's basically a very commonly used optimizer. We use it a lot in these slides. And epoch is a pass through our training data set. So that's every chunk that we saw in that graph, every blue dot. And as we go through and through, our optimizer will use our last function to help fit the model to that curve. And finally, we can ask for predictions by calling f of our new data. The layers API is a little bit cleaner. It's not so much in the weeds as I keep mentioning. This is actually a model we'll build tomorrow, but we want to use our layers API to do very simple speech command recognition, like one-word sentences, one-word bits. So using the microphone, I can say the word hello, and you hear the word hello, but there is an application or an existing framework called FFT that can actually build a spectrogram of a specific word. So that would be hello as a spectrogram. Yeah, there's hello. And we're going to build a convolutional neural network that uses image classification to learn how to recognize the word hello. I'm going to gloss over a lot of details here because it kind of gets a little complicated, but the first thing we do is declare a tf.sequential model. If anyone has ever looked at Keras or seen any Keras code, this is almost identical. A sequential model says I'm just going to have a series of layers. There's no recurrent networks or anything more complicated. It's very simple. And we're going to use a series, quite a few series of convolutional 2D networks. These are basically like Photoshop filters that are activated by the ReLU operator. It gives the model like 8 different versions of the image. And that's going through the convolutional network. That's how it knows to look for patterns. And the ... is the various variations of convolutionals and pooling. And I should say that we do have this as a all sample code on our TFJS examples repo. We're purely open source on this project. Last line is we're going to add a dense layer of softmax, which is the final layer that we're looking for however many words. So if we're looking for 10, num classes would be 10, like hello, cat, dog, red, yellow, and so on. The last API to really use once you've constructed your model architecture is just to compile it and give it a loss function. These are all defined in our API docs. We're going to use the SGD optimizer as well, and if there's any problems with our model, there'll be an exception on the console. Finally, once we have our model defined, we can fit it with training data and training labels. So XS is all of our images, and YS is all of the labels that match up to what word that was passed in. And then we'll train it 10 times. For those not super familiar, the await keyword is a newer JavaScript for awaiting a promise, and we use it quite a bit in our library. And finally, once our model's trained, we have the ability to save locally in Node.js and also in the browser using local storage. And last up, I can get some model predictions. So I wanted to show a quick in-browser demo real quick that uses this model. As soon as I click the start button here, there's a whole bunch of different boxes for different keywords and stuff. And it's kind of trying to pick up the words already. 3, 4, 4, go. Go. Up. Yes. Yes. So it picks up some noise. This is all a model you can run directly in the browser off of our examples repo. We have a link out and actually show you how to take this model and train it if you need different labels. That one's always fun to do in a conference room. It picks up stuff. And so finally, our models repo. This is the real fun stuff because you don't have to go through all the stochastic gradient descent algorithms and finding your fit to your curve. You can use stuff right out of the box today. So one of the models that we have is a speech commands model. And the API is very clean. There's really not a ton of ML required. So first thing we're going to do, we're going to use browser FFT. That's just use FFT in the browser. And model.collectExample. This is a callback to collect some examples where you can say the word red, green, or blue, or whatever label you want. So in this model, we're just going to train an audio model that can recognize red, green, and blue. And then we train it for 25 passes through that data set. And then we can start streaming results off of the model. And for each one, we listen for some audio. Those come out as labels, and we sort of just console.log with probability. So this is all off-the-shelf model you can use to get simple audio commands today. And again, it's all available over NPM. This one we've had it for a little while. It's still really cool. It's human pose estimation model. This is also available over NPM, already pre-trained. And all you have to do is find an image element in the DOM and ask PoseNet to estimate the single pose. And it gives you a JSON object with all the keyframes and the position of that picture and the score. We also have a demo on our site where you can open that up on your laptop now, and it'll, in real time, draw a figure of yourself off of the live video coming from the webcam. And finally, this is another model we recently open sourced. It's called Coco SSD. It's just a fancy term for find things in pictures with probability. Again, that gives you a whole JSON object of, is this a person or a kite or a box, and a probability score of what the model thinks it is. Lastly, I wanted to show an existing feature of the framework, which is taking a pre-trained model from the Python world and bringing it directly in the browser. At Google, we built this demo called the emoji scavenger hunt, and it takes a pre-trained model off of the MobileNet architecture, all done in Python, and we trained it to recognize pictures of things around the office that match up to emoji icons. And I actually have a video for this. And I'll play for just a sec.
This is an umbrella. So is this. This is a slice of pizza. So is this. Emojis have become a language of their own. We use them every day to communicate in our text and emails. So much so that it's easy to forget about the real-world objects they're based on. Which got us thinking, could we create a game that challenges people to find the real-world versions of the emojis we use every day? Introducing Emoji Scavenger Hunt. Emoji Scavenger Hunt uses Tensorflow.js. Open source meets machine learning meets JavaScript meets fun. It works like this. We show you an emoji. Use your phone's camera to find it before the clock runs out.
Hey, you found pen.
Find it in time, and you advance the next emoji. While you're searching, you'll hear our machine learning system doing its thing.
Do I see a toilet tissue? Was that a tub? Is that a glove? Hey, you found watch.
See if you can find all the emojis before the timer runs out.
Do I spy a broom?
Emoji Scavenger Hunt, powered by machine learning. Start your search at g.co/emoji scavenger hunt.
Do I see a URL?
So that just gives you an example of the really cool demos you can build. This is just this was a non-ML team that does a lot of creative work for Google up here in the city, and they just built this, and we kind of collaborated with them and helped them clean up a few things. So really cool stuff. I want to kind of show you how that process worked. So as I mentioned, it was a MobileNet. MobileNet is an image classification model, and all that was trained in the Python world. MobileNet itself is an object detector. It helps find things like watches and beer and all that sort of stuff. And then we ported it over to our front-end application called Scavenger Hunt. Now, as that model is trained, it is saved in Python world. So all the weights and the model artifacts are saved in Python. And in the TensorFlow world, we call that a saved model. And in Keras, it would be called a HDF5 model architecture. These are all two different Python stacks, but we both support these model formats. That model is saved, and we use it with our converter. This is a Python package we ship. So you pip install Tensorflow.js, and this tool here will help take that Python model and create JSON and serialize weight artifacts for the browser. And we have options as well for Keras. Now, once those artifacts are created, you can host them on your web server and just load out where the model URL is and the weights. So the model itself is just a very small JSON file that kind of describes all the architecture of the model. And the weights are all the parts, the hard work done in training, and those tend to be the larger bit. We actually shard those in 4 megabyte chunks, so they're really easily cacheable in modern web browsers. And once you load that in, we can run model predictions, and that's what that application's doing just over and over again, taking image off the web camera and running predictions. Again, this is the Keras style format as well. It's pure JSON. So in our model conversion step, we actually do a few things other than just take the graph and convert to an arbitrary format. We use some conversion of some graph optimization that helps shrink the number of ops that each model has to go through. And then, as I mentioned, we optimize those weights for the browser, so the 4 megabyte chunks. And currently we support a little over 120 plus of the common TensorFlow ops, and then 35 plus, so some odd of the Keras layers. And we're always working on this project. As new models come up, we implement new ops, and they land on our core API, and they're available to all other users. Now, training in the browser is something we have as well. I wanted to give you a quick benchmark of where we're at, and I have some slides to talk about performance and areas we're improving on the browser front. But the MobileNet model that we demonstrated in this emoji scavenger hunt uses MobileNet. So we have a benchmark of MobileNet we took with Python TensorFlow. So the bottom bar is the Python CPU build of TensorFlow. And this is run on like a MacBook 13-inch Pro. And the top one is a high-end workstation with an NVIDIA 1080 GTX card. That's one of the top-of-the-line NVIDIA cards. And it uses Python with the CUDA library. So this is inference time for 200 runs of an image. The same, I think it was like a cat picture. It wasn't anything exciting. And so on the MacBook, we were seeing 56 milliseconds per inference time, and obviously super fast on the NVIDIA card, 2.8. So that was our baseline benchmark of Python. Now running those same benchmarks with using TensorFlow.js in a Chrome browser on the same hardware, we were seeing that the 1080 GTX machine was really close to the CUDA library. It was 5 millisecond inference time. And on a laptop that had an integrated graphics card, the shared integrated CPU, GPU, we were seeing it is a little faster than the actual CPU of the MacBook. So the performance is pretty good, and 50 milliseconds is enough for like a real-time live demo, and that's everything we've been running. And we're working on some specs, and I have some stuff to talk about that later down the road. On the server side, we do support the full Node.js stack today. We see a lot of opportunity with the NPM ecosystem. There's tons of packages, and it makes it really easy to piece together a really deployable, interesting server-side solution. And NPM and the open source community is awesome for that. So we think bringing ML to this space will bring some really cool demos and projects. The default interpreter for Node.js V8 is super fast. We've seen it up to 10 to 20 times as fast as the Python interpreter. And thanks to organizations like Google, the Chrome and the V8 engine is always improving and getting faster. The other opportunity is access to hardware. This means ML accelerators, TPUs, GPUs, edge TPUs, and other things as they're coming along the line. I want to show you exactly how it's really easy to use this library in Node.js. We've sort of cleaned this up over the past few months. This is a Express application, a request response handler, very, very boilerplate. And all we have to do to use TensorFlow with the node bindings is just import this package. And then now we're running it with accelerated hardware. And we just call a model.predict. And if your server architecture has the CUDA NVIDIA library, we have that package available. It's just a little differently. The API is exactly the same. It just provides CUDA acceleration. So today in Node.js, you can port existing models and run inference. And we also have builds for macOS, Linux, and Windows for CPU. And then the CUDA stack is Windows and Linux only. And again, the full library of Tensorflow.js all runs under the Node.js runtime. And again, I wanted to show that same benchmark to show you where we sit within Node performance. This is that same benchmark, MobileNet, the same numbers. And obviously, since we're running on the C library that Python's executing, we're pretty much on par with the benchmark. So if you need a Node solution that uses ML for inference, the Tensorflow.js Node bindings is a really good solution today. One of the other cool projects one of our colleagues has been working on is a visualization library for machine learning. And this is an all pure in-browser API for drawing what's going on inside those convolutional 2D layers. There's an element you can bring in called the drawer or the visor, and it gives you visualization for all these different things. That Photoshop filter I was telling you that Com2Ds do, the TFJS Viz library actually draws those in the browser for you. It's really cool from a learning and like debugging technique for figuring out what's going on in your models. We also have a bunch of built-in charts to see if your data is skewing towards one class or the other. And then just high-level visualization, we have a bunch of examples that kind of show you how to load this library in and start visualizing things today. So I've shown you a lot of stuff. We've done a lot over the past year or so, and I want to go over the things we want to do coming up next. From like a general platform perspective, we're going to continue investing in our visualization library. We also just recently launched the data API, TFJS-data. It's a streamlined process for bringing in CSV data to your models. You don't have to do any conversion or flatten tensors or anything crazy like that. It's also a really cool utility if you're running a node and you need to do some basic data processing. We have that library and we're continuing to invest in it. The other really cool part that we've been starting to look at is taking our WebGL library and bringing it to other platforms like React Native, Electron, and then running these accelerations as like a headless GL library. So we've open sourced a GLES library that uses Angle, which is the WebGL Chrome runtime, and we're looking to bring that as a headless node solution for everything like IoT devices and React Native and so on. In the browser, we've been focusing a lot on two main components. One is bringing more of those easy-to-use models, like the Cocoa SD, the speech commands, definitely focusing more on the audio and like text sentiment analysis models. So models that you can throw in your browser and look at a grouping of text and make an analysis from that. The other interesting thing we've been doing is focusing more on the performance area. Some of that is not using WebGL as much, but looking at technologies like WebAssembly, WebAssembly with AVX, compute shaders, and a couple of us on the team are participating with the W3C to help push the WebML and WebGPU standards forward. So a lot of stuff that's kind of coming down the pipeline on that front. And on Node.js, we're focusing a lot on the cloud integration story, making it really easy to spin up a async function in the cloud. We're bringing all of the core TensorFlow ops to the library as well, and async support to help our callbacks so we're not blocking the UI thread. And to wrap up, we have our core API that's kind of the in-the-weeds linear algebra library, our layers or Keras style API for building models today, our super high level models repo, the out-of-the-box machine learning models you can use. We support conversion of the TensorFlow save model and Keras models, and our Node.js story. And of course, the Viz library we just launched. And with that, I'd like to thank you. All of the stuff I've shown you is pure open source. This is our root GitHub page. We have a bunch of different projects, but this is our main page where we have issues and discussion, as well as links to our models repo examples, community built examples, and that sort of thing. We also have a mailing list as well. This is a little bit sort of like soft deprecated. We prefer that this open on Stack Overflow, so if you have questions, tag in there. Our gallery is community built examples. This is available on our website as well in the models repo. With that, I think we have a little bit more time, so if anybody has any questions, feel free to ask. like an OpenCL type infrastructure. It's something that's been looked at, but we have a sister team called Tensorflow Lite, and they are sort of looking at an OpenCL interpreter runtime on top of that, but there isn't anything concrete on that front today. Cool. Thank you all.